Okay, how many of you learned about virtual memory before? Okay, not many. That's good. There are some people, okay, so you know, that's good. But not many. So you will learn more about this when you take the systems programming course, because operating systems rely on virtual memory very heavily. So let's see if we can finish it in the remaining amount of time. So there's some reading associated with it. It doesn't go into a lot of detail. It gives you the basic ideas. So this is the programmer's view of memory, actually. You do a load from memory and you do stores to memory. And so far, we've assumed that memory is physical, right? You basically have the address that you have in memory, the programmer knows that address and accesses it. But if you remember the ideal memory, we want zero access time, infinite capacity, zero cost, and infinite bandwidth. So now we're going to deal with capacity issues. What if you don't have enough memory? Okay, so basically we have an abstraction. So far we've assumed everything is physical, but in real life actually, a programmer sees virtual memory. Now what does this mean? This means that the programmer can assume memory is infinite. So if you have a limited size memory, you can provide the illusion to the programmer that there's actually a lot more memory, so that the programmer doesn't need to manage memory. So it's another example of a classic programmer microarchitect trade-off, and you need to have this so that the programmers don't go crazy. So, okay, reality is that physical memory size is much smaller than what the programmer assumes. You have, I don't know, let's say a 2 gigabyte memory, but if you look at the address spaces today, it's 2 to the 48, which is much larger than 2 gigabytes, or 2 to the 64 if you push it to the limits. And the system provides the illusion to the programmer that physical memory is actually infinite, or memory is equal to the space that's specified by the ISA somehow. So when I say the system, it's the system software and the hardware cooperatively together. They basically have a mapping internally that map the programmer-specified addresses, virtual memory addresses, to physical memory addresses. So physical memory is where the data really is. Virtual memory is the address that the programmer uses to refer to that data. It doesn't mean anything actually. Virtual memory address is some name for the data that the programmer is trying to access, and internally that name gets mapped to a particular location. That location could be in main memory, it could be in the disk. So the system essentially automatically manages the physical memory space transparently to the programmer. The programmer actually doesn't manage the physical memory at all. Okay, so what's the upside? And we're going to go into the details, of course, progressively. This way, the programmer doesn't need to know the physical size of memory, nor do they need to know to manage it, right? Actually, when you write programs, you don't need to know the size of your physical memory. Of course, if you know it, you can probably write programs that are smaller as much as possible, but ideally you would like to make your programs as small as possible anyway, right? This means that a small physical memory can appear as a huge one to the programmer, and life is easier for the programmer. So how are we going to provide this illusion? Well, we're going to provide this illusion by making the system and the architecture much more complex, essentially more complex system software and architecture, and we'll see that complexity in this lecture. And as I said, this is a classic example of the programmer microarchitect trade-off. It's perhaps one of the most successful examples. Cache coherence is one example, but this is maybe even more fundamental. It's one of the most successful examples where the hardware architecture and system software together provides a programmable machine to the programmer, such that the programmer doesn't need to worry about running out of physical memory. Okay, so what's the benefit of automatic management of this physical memory? Programmer doesn't need to deal with physical addresses. Each process also has its own mapping from this virtual to physical addresses. We're going to see that mapping in more detail. This enables multiple things. One key thing is code and data can be located anywhere in the physical memory. Because you manage this mapping at the system software level. You take these virtual addresses that the programmer just gave you, and then you can map the virtual addresses anywhere in the physical memory, right? The programmer doesn't need to deal with that, basically. The programmer doesn't try to say, okay, this data gets mapped, this particular piece of data gets mapped next to this particular other piece of data, ... It's the system's job to do that mapping. And this enables relocation. If some part of physical memory is not available, you can put the program into other part of physical memory. That's called relocation. And this is essential for system management. This also enables isolation of code and data of different processes in physical memory. So let's assume that programmer X writes a program and programmer Y writes a program. They both use addresses from 0 to, I don't know, 5,000. Now both programs run together. If these were physical addresses, you have a problem, right? Both of the programs say address 0. But these programs actually have nothing to do with each other. One is running a virus checker, the other is running, I don't know, your favorite game. I guess Angry Birds is not as popular anymore, but that game, right? They have nothing to do with each other, but the programmers use addresses 0 to 5,000. If programmers actually use physical addresses that really indicate real addresses in the machine, this would not work. But what the system does is, it basically translates those addresses. These are virtual addresses, even though they're between 0 and 5,000. The system says, this program 0 and 5,000 goes to this part of physical memory. This other program 0 and 5,000 goes to this part of physical memory, so they're isolated from each other. They're completely separate, and they're protected and isolated from each other. Right? That's the idea. So that level of indirection between virtual addresses and physical addresses enables the system to ensure different processes are isolated. And also you can apply different protection mechanisms. So you can say this process can access only these parts of physical memory, right, through that mapping. We will see that. This also enables code and data sharing between multiple processes. Basically, if the processes actually need to share the data, different virtual addresses, different addresses in different programs can be mapped to the same physical location. It's really what that data is that matters. It's not the name that matters. As long as you map the name of the different processes to the same data, you don't have a problem. This will become more clear with some of the pictures that you will see. Basically, we have a level of indirection. The programmer doesn't get exposed to the physical addresses directly. The programmer does virtual addresses, and the system maps those virtual addresses to physical memory. And as a result, it enables all of this. Okay, so let's look at a system with physical memory only. Basically, whenever you access memory from the CPU, you use a physical address, so there's no indirection, there's no translation that happens. So old machines actually used to have that. Many embedded systems still have that. The load and store addresses directly access this physical location. Whenever you say load from address 0, it's really address 0 in that particular location. And if you have two programs that's loading from address 0, too bad. And they're not supposed to share data, it's too bad. They conflict with each other. So somebody needs to ensure that they don't conflict with each other. So this is not easy to satisfy. So the problem is basically, there are multiple problems with it actually. Let's go through some of those problems. One is physical memory is of limited size because it's costly to have a lot of memory. Especially historically, you had very little physical memory. Today, we actually have a lot of luxury, right? We have machines with 8 gigabytes actually. I already have 8 gigabytes, I think, in this one. We have machines with 32 gigabytes of memory. That's a lot. In the past, it was 1 kilobyte, 2 kilobytes, 4 kilobytes. So physical memory is of limited size. What if you need more? You have 32 gigabytes, okay. But what if the program needs more? What does the programmer need to do if they run out of memory? That's a problem, right? So now the program needs to manage the disk, manage bringing data from the disk into the physical memory, and then manage putting data from the physical memory back into the disk. That's a lot of effort, actually, because you run out of physical memory. So should the programmer be concerned about the size of code, data blocks fitting physical memory? No, if you want to actually make programmers program efficiently. Should the programmer manage data movement from disk to physical memory? Again, no. Should the programmer ensure two different processes do not use the same physical memory, assuming they are not sharing data? Actually, this is one of the toughest parts. Okay, the programmers may be able to manage that. There used to be mechanisms for overlay memory management such that the system helps the programmer a little bit to manage this in the past. But this is really hard, actually, if you don't have a lot of support, because the programmer uses some addresses, another program uses the same addresses, and you need to ensure that they don't conflict with each other. And also, the instruction set architecture can have an address space that's greater than the physical memory size. So it can have 64-bit address space with byte addressability. So 64-bit address space is 2 to the 64 bytes if it's byte addressable. The ISA specified this. But physical memory may not be as large, right? Physical memory may be 4 gigabytes only. 4 gigabytes is 2 to the 32 bytes. Now you have a problem. The programmer can actually use any of those bytes in the huge address space, 0 to the 64, but the physical memory is not there. So somebody needs to ensure that the program runs correctly, right? So you need something in between the programmer's addresses and the real physical structures of memory. So basically, if you don't have physical memory, it just doesn't work. Okay, so there are multiple difficulties of this direct physical addressing. As I said, programmer needs to manage the physical memory space. This is inconvenient and hard. It's doable, but it's a lot of effort to decide when you're running out of physical memory, what you should put into the disk, and what you should bring from the disk into the physical memory. It's harder when you have multiple processes. You can imagine this. It's difficult to support code and data relocation. If you want to relocate the data somewhere and code somewhere so that things don't conflict with each other, now the programmer needs to deal with this because the addresses are directly specified in the program. And it's difficult to support multiple processes. As I said earlier, protection and isolation between multiple processes is difficult. And sharing of physical memory address space is also difficult in this case because you need to ensure the exact addresses are used in different programs. And I already said this also, actually. Data and code sharing across different processes is difficult. So the basic idea of virtual memory is actually very, very simple. You give the programmer the illusion of a large address space while having a small physical memory, such that the programmer doesn't need to manage the physical memory. And this leads to multiple benefits. One is the programmer can assume he or she has infinite amount of physical memory, as specified by the ISA. If the ISA specifies 2 to the 64, that's great, and that's a lot of memory, actually. And the hardware and the software cooperatively and automatically manage the physical memory space to provide this illusion to the programmer. And illusion is maintained for each independent process separately. Because each process is written separately, and you use some virtual addresses, and the system maps those addresses to physical addresses. So the basic mechanism is actually very fundamental and simple. We're going to use indirection in addressing. And the address generated by each instruction in a program is a virtual address. It's not a real address that you can say, okay, this address is in this particular structure over here. You cannot say that because it needs to be translated to that. Basically, it's not the physical address used to address main memory. This is also called linear address in x86. There are some terminology issues. x86 uses linear address for this. And there needs to be an address translation mechanism that maps this virtual address to a physical address. And that's where the magic lies, basically. That address translation mechanism can be designed intelligently so that it can fix all of the issues that we've discussed. This is, the physical address is called a real address in x86. Actually, I really like the real address because it's really the real address that you're addressing the physical structure with. An address translation mechanism can be implemented in hardware and software together. In today's systems, it's actually implemented cooperatively between the hardware and software. And this is one example where hardware-software cooperation has been very, very helpful. Because if you implement this purely in software, it becomes extremely slow. And you cannot fully implement them purely in software. You have to have some basic support, actually. So, okay, this is the picture, basically. We changed that as opposed to CPU directly accessing, generating physical addresses. This is what is going to happen. We're going to add another structure called a page table. A page table is associated with a single process. Each process is its own page table. And the purpose of the structure is to the address translation from a virtual address to a physical address. So the programmer uses virtual addresses. They can do whatever they want with the addresses. And the system maps those virtual addresses to physical locations. So for example, basically the hardware converts virtual address into physical addresses via an OS-managed lookup table. So this is an operating system-managed lookup table. It's called the page table. Whenever you generate the address, let's say X over here, you consult this page table, and the page table says, oh, this address is in physical memory location Y over here. If you generate an address that maps to this location, let's say a virtual address, I don't know, 10,000, the page table, this address may not be mapped to physical memory yet. It may reside on disk. And the page table will tell you, okay, it's not in physical memory, it's actually in disk, so I'm going to bring that address into the physical memory first before you can access it. And this is all done automatically. The programmer doesn't need to manage the data movement between disk and the memory, and the system does the management. The programmer just codes with virtual addresses. So that's the idea over here. You have this indirection layer that maps each virtual address to a physical address. Does that make sense? Now this enables multiple other things, not just mapping, but also access protection. Now you can add bits to this page table entry. So this is called a page table entry because we're going to manage this at the granularity of pages. Pages are larger granularity than cache blocks. Now you can actually say, okay, I have access permissions, particular access permissions to this page. I can execute this page, for example. I can run code on this page. Or I can basically mark the page as data page, so you cannot execute that page. That actually turns out to be important for security purposes, because you don't want everything to be executable in the entire virtual memory address space. Okay, so let's go into a little bit more detail now. Basically, virtual address space is divided into pages, just like I've described over here. We're going to talk about the page size. Usually it's 8 kilobytes or 4 kilobytes. But then today, there are actually bigger page sizes as well. Physical address space is divided into frames. And a virtual page is mapped to a physical frame if the page is in physical memory, or a location in disk otherwise. So basically, that's the mapping that you have in the page table. If an accessed virtual page is not in memory, but it's on disk, the virtual memory system, hardware and software cooperatively, bring the page into a physical frame and adjust the mapping. This is called demand paging, and most systems today have demand paging. So it's done automatically, completely transparently to the programmer. And the page table is the table that stores a mapping of the virtual pages to the physical frames. So in other words, we're using physical memory as a cache to the disk, right, in this case, right? Everything starts out, it's in the disk, and we slowly start bringing data into the physical memory and mapping data into the physical memory. So a physical memory is a cache for pages that are stored in disk. In fact, it's a fully associative cache in modern systems. A virtual page can potentially be mapped to any physical frame. That's the definition of a fully associative cache. And similar caching issues exist, as we've covered earlier, actually. Basically, where and how do you place or find a page in cache? What page to remove to make room in your cache? If your physical memory is full, what do you kick out if you want to bring in another page from the disk into the physical memory? That's essentially a cache replacement problem, actually. Granularity of management, what should the size of a block or frame or page be? What should the write policy be? Basically, what do you do about writes? Whenever you write to physical memory, do you also write to disk? Probably not a good idea. Actually, physical memory is a write-back cache to the disk in existing systems because the latency between physical memory and disk is huge. It's orders and orders of magnitude, actually. Physical memory is in nanoseconds, hundreds of nanoseconds. Disk is in milliseconds. Or with SSDs, it's actually microseconds right now, but still, it's orders of magnitude. Okay, so basically, there are analogues between the cache and virtual memory terminology. A cache block is the same as a virtual memory page. Block size is page size. Block offset is page offset. Whenever you get a cache miss, in the physical cache, it's a miss, but if you get a miss in physical memory, that's called a page fault. Basically, you miss in physical memory. This means that the page that you're looking for is not in physical memory, it's in the disk. So you get a fault, and somebody needs to bring the page from the disk into the physical memory. And that is done by the operating system today with some hardware support. And tag, so clearly you need to identify whether a location exists in physical memory, and we use the virtual page number for this purpose. So let me give you a couple of definitions, and then we're going to go into a couple of examples. So page size is the amount of memory transferred from hard disk to DRAM at once. DRAM is a physical memory, that's the assumption here. Address translation is the process of determining the physical address from the virtual address. It's obvious. And we already defined the page table. It's really a lookup table used to translate the virtual addresses to physical addresses and to find where the associated data is. So this is another view, basically. This is really, these are your virtual addresses. There is a magic over here, address translation through the page table. And some of the pages are mapped to the hard disk. Some of the pages are actually in physical memory. And the hope is that most accesses that you do hit in the physical memory. But programs see the large capacity of the virtual memory. Basically, your disk can be terabytes and terabytes and terabytes, right? That's bigger than actually your address space in your ISA. So as a result, you don't need to worry about the size of your physical space. And this is how the translation is done. Basically, this is assuming that you have a 31-bit virtual address and a 27-bit physical address space. And assume that you have a 4 kilobyte page. The last 12 bits are actually the page offset, and this is byte addressable. The page offset doesn't change, but you basically translate the virtual page number to physical page number, or physical frame number. I use frame and page interchangeably here. And this translation happens through the page table. Essentially, you index this data structure called the page table with the virtual page number for that process. And the page table tells you if this location is in physical memory, it gives you the physical page number. And the offset is exactly the same as the virtual offset that you have over here. So let's take a look at an example. Assume that your virtual memory size is 2 gigabytes to the 31 bytes. If your physical memory size is much smaller, to the 27 bytes. And assume that page size is to the 12 bytes. Page size is given by the ISA. And actually, existing ISAs have multiple page sizes. Let's go through this example, and then I'm going to be done. So the organization, virtual address is clearly 31 bytes. Physical address is 27 bits. Page offset is 12 bits. So you can easily get the number of virtual pages. You divide 2 to the 31 by 2 to the 12. That's 2 to the 19. As a result, virtual page number is 19 bits. And physical pages 2 to the 27 divided by 2 to the 12. Physical page number is 15 bits. And this is the mapping that you have from the virtual memory to physical memory. And I think we're going to continue from this point tomorrow. I'll see you tomorrow.